Good morning, everyone. Thank you all for coming this morning. I want to get started right away so that I can respect your time and get us out of here. Time for lunch. My name is Sasha Kopp, and I'm glad to have you all here this morning. I wanted to, in the next few weeks, present to you some of the resources that the college has been preparing for faculty as they think about other ways to work on their classes. And for myself, I would like to maybe start this by talking a little bit about the kinds of teaching models that at least I'm familiar with that might benefit from using this. And I asked Cynthia LeBrake from the Department of Chemistry to come in and talk to us about one of the classes that she has been working on, and I'll talk to us a little bit about the class that I've been working on, or a couple of classes I've worked on. And that's not to say that that's the unique solution to all teaching in the college, but merely to help us wrap our heads around various models that might make use of some of the resources that the college has been developing in Quest, and also in the area of assessment and using Mathematica, and also in videotaping some of our lecture content. So in the next couple of weeks, Cynthia and I will be talking this week about the courses that we've been working on and how we make use of some of these resources used by or developed by the college. And then next week, a couple of our postdocs on the Quest team will talk a little bit about the videography and capturing of lecture content that you might consider using as resources here in the college. And then the week following, another one of our postdocs will talk about how to write assessment questions using Mathematica, because I think many of us who have experience with Quest are prone to think of it as a multiple choice question bank, which I think up till relatively recently is a good reflection of what it was. But we've tried to flesh out the kinds of questions that you can put into it. And I know that some of the challenges I've been wanting to give the Quest team is how can I literally get to the point where I can use Quest to have, or can I use Quest to grade an assignment that looks like derive an expression for the following thing, and get back to that kind of hand-graded homework that we can't afford to do because we don't have enough TAs in the college to do all that kind of grading for thousands and thousands of students. So, you know, that would be sort of the pie in the sky, but I'd like to at least think about ways to use Mathematica for a little bit richer kind of problem solving than we're capable of doing right now with the multiple choice question games. So I thought I'd talk a little bit first about some of the classes I've taught. I've taught senior level quantum mechanics here in the college. I've taught ostensibly freshman physics, but mostly taken by our pre-meds. I've done some sophomore modern physics classes taken by engineers and by physics majors. And across all these varieties of classes, I would find myself carefully preparing a summary of what they should know. And since physics is a fairly mathematics-intensive subject, I'd write out careful derivations of where all these important equations come from. And I do a couple example problems and show how to solve a problem using those important equations. And then I go give the students a question on a homework and expect them to come back a week later having the capability of solving that homework. And in preparing for lecture each day, I would probably look at the textbook a little bit, but I would have assigned them some reading to do. And I would probably have consulted some other texts and probably try to look smart by having a completely different derivation from the textbook that they read by copying down a derivation from some other textbook. Oh wait, that's the secret. I'm sorry. I'm not supposed to say that. But I remember one time someone made me aware of a tool in physics called the Force Concept Inventory. It was written by a group at Arizona State, I believe. And it had some basic questions which to the physicists here in the crowd will look very familiar. And we were encouraged as instructors to give this assessment at the beginning of our semester and at the end of our semester. And this assessment doesn't consist of anything particularly calculational, or it doesn't require a genius level of calculus to do anything. You know, question 25 down there just refers to that picture, and it says if you've got this bead shooting through a little tube that's round, where does the bead go when it comes shooting out of the tube? And all the students have to do is pick the correct trajectory of those 5 choices. And it was interesting to note at the beginning of the semester that the students would randomly have selected any one of the 5 choices with basically equal probability. And at the end of the semester, I'm happy to report that they chose each of the 5 choices with equal probability. Despite the fact that this represents a problem which is, in a fairly basic sense, a centripetal motion problem in physics, and all of us instructors dutifully cover it in our class. We derive why it's so that Newton's second law of motion requires an object to move in a circle requires a centripetal force. An object without such a centripetal force keeps moving in a straight line. So the correct answer is B, for those of you wondering.
I do remember something.
You do remember something like that, yeah. I was further ashamed to see that actually, although the students did slightly better than guessing on this assessment before taking my class, they did only 1 point better on this assessment after taking my class. So there were some rather notable failures on the semester, and you kind of wonder, why did they take my class? But they clearly did do something in the class. They learned to do lots and lots of calculations, and they learned to do them correctly to the next digit on exams. But there are some basic things that at least all of us physicists would feel like were important that they failed to grasp. And I guess for me it was the first encounter with the idea of, okay, there's some goals that I would like to have in the class, and maybe, without necessarily wanting to teach the test, I'd like to at least structure my class such that the students would meet a certain goal. I am happy to say that I'm not alone in this experience. There are published journal articles about the force concept inventory and about how many classes actually result in negative progress on this, this assessment. It's actually a pretty good assessment. It has a pretty good understanding of what should be in a first-year mechanics class in physics. But I think it's because so few of us structure our classes around learning outcomes that we end up not really achieving the kinds of things that implicitly we would hope for in a class. And I began to wonder, okay, so is it the case that in my class I should somehow structure the time to look at these conceptual problems better, or should I be spending the time doing all these derivations and mathematically intensive things? Because the instructors who follow me in a sophomore physics class would really rely on students being able to solve complex integrals and being able to apply them to richer problems, even more complicated than what we should be doing in a first-year physics class. So it's not the case that I want to set this the calculus-heavy physics aside in order to do these kind of conceptual things, because that is a skill that is ultimately required. But I then think about some other things that I've heard many people say, and David Lally in our college talks about this often. Instructors have a pair of roles in teaching a class. They have this sort of delivery of content kind of role, and they have this role as mentor and facilitator, and that's another role to be thinking about. And I thought, maybe in more crude terms than David has articulated it, that we have some things that we can do outside of class and some things that we can do inside of class. And for me, my personal introduction to this kind of topic came from the following textbook, which is, again, a physics book, so it's maybe not one that translates to all subjects, but it's written by Eric Mazur at Harvard, and it's called Peer Instruction. And the thing I like about this book as a model that's maybe generally approachable for all of our science classes, and he wrote this book before the web, so, well, not before the web, but before we use the web as much as we do now, so it has these great things called floppy disks. I keep them in here, they're still taped in there. So for those of you too young to know, before computers, in the early days of computers, you would stick this thing in your computer and it had data on it, as much as kilobytes apparently. Yeah, so this is the day before thumb drives and email. In any case, Eric's proposed model for a class that he developed throughout the 90s and then wrote about in this book was one in which he was trying to do more active engagement in the class and try to think of himself as more this facilitator and coach in the class and relegate the content delivery to outside of class. And again, because this is almost before the web, he very much relied on textbooks as his model, but he had some very good ideas that if we're trying to teach students how to read textbooks and how to really assimilate the information from a textbook, let's really drive that skill into them. And he would begin every class with something he called a quiz, if we still have those in class. But he had these conceptual quizzes, and to give you a sense, let me just